Hello, this is Module 5, Lesson 6. Today we're using tree diagrams to represent sample spaces, and we're going to calculate probabilities. So, how can we use a tree diagram to determine the probability of events? Okay, this is kind of long, but it's a pretty simple, I don't know, concept what a tree diagram is, and we're going to kind of jump around on the pages. So the first thing that we're going to do is we're going to talk about this scenario. There's a girl that attends a preschool and they're studying primary colors. So think real quick if you know what primary colors are. To help teach calendar skills, the teacher has each student maintain a calendar on his or her cubby. For each of the 4 days they are covering a primary color in class, the students get to place a colored dot on their calendar, either a yellow, red, or blue. Okay. When the 4 days of the school week have passed, so it sounds like they're only in school Monday, Tuesday, Wednesday, Thursday, what might the girls' calendar look like? So what it's saying is, after the 4 days, what could the calendar look like? Okay, so it's saying there's 4 days, and in each day they get to do a colored dot. Okay, it might be a red dot, it might be a blue dot, it might be a yellow dot, it might repeat one of them. So it's just saying what might the young girl's calendar look like. One outcome would be 4 blue dots. Okay, so we could have, instead of this, we could have blue for all of them. Blue, blue, blue. It could be all 4 blues. Okay, that's one option. So it could be blue, 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 blue. Okay, each one of these is Monday, Tuesday, Wednesday, Thursday. So I'm not going to leave those up there, but just so you know, they get one of the 3 primary colors each day. So you're just trying to see like what are all the possible options. Okay, but what if the first day, Monday, was blue, and the next day was yellow, and the next day was blue, and the following day was red? Or maybe Monday and Tuesday could be yellow, Wednesday could be blue, and Thursday could be red. Or Monday, Tuesday, and Wednesday could be blue, and Thursday could be red, so on and so forth. Whew. Okay, that's going to take us a really long time to do. As hard as it is to follow, we've only mentioned 3 of the 81. I guess they're not counting this one when they say they've mentioned 3 of 81. So that's 3 of the ways that it could be. So there's 81 total combinations. Are we going to list out 81? No, because this video would be a lot longer and it wouldn't really be productive. Okay, that would take several pages. Rather than listing outcomes in the manner described above, particularly when the situation has multiple stages, such as multiple days, we often use a tree diagram. And actually, even for this one, I think that the tree diagram would be too confusing. Okay, so I actually think that the tree diagram has too many branches here. The way that you could see it is, I'm only going to do the first couple stages. Okay, a tree diagram looks like this. The first day could be blue. Sorry, I actually made too many branches there. The first day could be blue. The second day could be red. Or sorry, I'm going to have to say that again. Okay, this is on the first day. So the first day could be blue, red, or yellow. Okay, then on the second day, it could be blue, red, or yellow again. Blue, red, yellow. And you actually make that branch off of each of these. Blue, red, yellow. Blue, red, yellow. Now, we're actually going to stop after the next day. So far, what it's saying is the first day could be blue and the second day could be blue. Or the first day could be blue and the second day could be red. Or if the first day is blue, the second day could be yellow. So far, that's only after 2 days. We could have that same mentality when we go down here and we talk about red. You could have red first and then blue. You could have red first and then red again. You could have red first and then yellow. And then on the last one, I'm going to try to hover over that one so I don't have to draw so much. You could get yellow on the first day and blue on the second day. You could get yellow on the first day, red on the second day. You could get yellow and then yellow again. Do you see how this can get out of control, or just how there's maybe many more combinations than you thought? So for the third day, it could be blue, red, yellow. Off of each of these, we would do blue, red, yellow. 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 So hopefully now you realize why there's no way that we could have actually listed every single one of them. This is only after 3 days, and it's already so crowded. So really, I think a tree diagram would be too much to do another branch, because then I would have to do blue, red, yellow off of all of those. Okay, so you could have blue, 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 red, blue, blue, yellow, blue, red, blue, blue, red, red, blue, red, yellow, blue, yellow, blue, blue, yellow, red. Okay, it's dizzying thinking about all of that. One way to figure out how many combinations there are is on the first day there's 3 choices, blue, red, or yellow. On the second day there's 3 choices, blue, red, or yellow. On the third day there's 3 choices, blue, red, or yellow. And on the fourth day there's 3 choices, blue, red, or yellow. And if you multiply 3 times 3 times 3 times 3, you get 81 possible outcomes. If I were to ask you how many possible outcomes you think there are in this scenario, most people think that there are only 12. A lot of them do 3 times 4, but it's not 3 times 4. It's 3 multiplied out 4 times. And as you can see, there are way more than 12 options or outcomes because we haven't even done the final branch, okay? In fact, right here, one more branch off of each, double underline each of these. Right now, this is only 27 actually, because there's 3 here times 3 here times 3 here. That's 27, and you can count it if you don't believe me. There's 27 different outcomes after 3 days, because that would be 3 times 3 times 3. But this has 4 days. So that is a lot, okay? We're going to do a tree diagram with a much simpler explanation, and that one is actually at the end on page 44. So go over here where it says 2 children. This is one that you may have seen before, or you can think of this in your own life. Maybe if there are 2 kids in your family, or think of a family that has 2 kids. Are you thinking of a family that has 2 kids? Oh, that aren't twins. Sorry, we have to clarify that aren't twins. Okay. 2 friends meet at a grocery store and remark that a neighboring family just welcomed their second child. It turns out that both children in this family are girls, and they are not twins. Okay, so they are both girls. One of the friends is curious about what the chances are of having 2 girls in a family's first 2 births. So what it's saying is if a family has 2 girls, if the family has 2 kids, one and then they have another kid, what is the chance that they will both be girls? Okay, we're going to draw a tree diagram first. When you have a baby, there's about a 50-50 chance, it's a 1/2 chance of having a boy or having a girl. Okay, what if you have another one? So if you had a boy first, you could have a boy second, which is my personal favorite combination. Or you could have a girl second. So you could have a boy, then a boy, or you could have a boy, then a girl. The other side here says, what if you had a girl first? You could have a boy for your second, and you could have a girl for your second. Okay, so the outcomes look like this. You could have boy, boy, you could have boy, girl, you could have girl, boy, or you could have girl, girl. So how many different outcomes is that? It's 4 different outcomes, and the chance of each one, so the chance of having a boy is a 50% chance, or 0.5. The chance of having a girl is 0.5. And same thing on the second one. Okay? So each one of those we consider a 0.5 chance, or 50%. So what we can do, girl, girl, there's a 0.5 chance of having a girl first, and a 0.5 chance of having a girl second. But to have a girl and a girl is 0.5 times 0.5, which is 0.25. And you all know that that's the fraction 1/4, because look at this. This is 1 out of 4 for a girl, girl, the one that they're asking about. Okay, so that actually is this one, right in the probabilities of each stage's outcome in the tree diagram. The other way we can write it is it's a 1/2 chance of having a girl, and it's another 1/2 chance the next time. So 1/2 times 1/2 is 1/4, and we know that that's 25%. Okay, and then make sure when we're done with this that you come back to the summary. We're going to do another example that's a little trickier. This family decides to play a game each night, and we're on page 42. This is example 1, but I actually think examples 1 and 2 are a little trickier than the one about the boy-girl. And by the way, that question, you could have phrased it with boy-boy, or you could have said boy first, girl second, or you could have said girl first, boy second. So it could have been the same answer based on the other outcomes. Okay, for example 1, 2 nights of games. Imagine that a family decides to play a game each night. They all agree to use a tetrahedral die. That's a 4-sided pyramid here, like if you can imagine, like the bottom is a triangle and the 3 sides are a triangle. And they decide whether they're going to play board game B or card game C. The tree diagram maps out all the possible outcomes over the 2 consecutive nights. Now, when I first read this, I thought, why are they using a 4-sided die? Why don't they just use a coin? And we actually find out in example 2, because I was a little impatient with this. I thought, why are they using a 4-sided die if there's only 2 options? So what we're going to do first is we're going to look at the tree diagram, and then on the next page, we're going to realize why they don't use a coin. Okay, so on Monday, they roll the dice, and they either are going to play a board game or they're going to play a card game. Those are their 2 options. So let's say on Monday they play a board game. What could happen on Tuesday? Well, they could play another board game or they could play a card game. So they're choosing each night by chance if they're going to play a board game or a card game. Now, if Monday they play a card game, Tuesday they could play a board game or they could play another card game. Okay, hopefully that makes sense, and it's filled in below, but I think it's good for us to write it ourselves. So you could play board games on both nights. You could do a board game Monday and a card game Tuesday. You could do a card game Monday and a board game Tuesday, or you could do a card game both nights. Hopefully that makes sense. Then down below, it says if BB represents 2 straight nights of board games, what does CB represent? Well, we just said that, so you write that in. What does CB represent? That's a card game Monday. And board game Tuesday. Okay, list the outcomes where exactly one, underline that there, exactly one board game is played over the 2 days. Well, if you play a board game on Monday and a card game Tuesday, that's exactly 1 night of board games. Or what about the other way around? If I do a card game Monday and a board game Tuesday. Okay, so there are 2 outcomes that show exactly 1 board game being played. So you could think of these as similar outcomes, except it depends on what day of the week. Just like with the kids being born, there's 2 outcomes where there's 1 boy and 1 girl, but it depends on, you know, which one, if you're saying the boy is first and the girl is second, or the girl is first and the boy is second. Okay. So now let's look at the next side, which talks about the probabilities here. On the example above, each night's outcome is the result of a chance experiment. Rolling this die. And again, as I'm reading this, I'm thinking, why aren't they flipping a coin? Okay, so there's a probability associated with each night's outcome. By multiplying probabilities of the outcomes from each stage, we can obtain the probability for each branch of the tree. In this case, we can figure out the probability of each of the 4 outcomes, BB, BC, CB, and CC. For this family, a card game will be played if the die lands showing the value of 1. Okay, that's for a card game. And a board game will be played if the die lands on showing 2, 3, or 4. So the way I see it is, let's say I'm the mom And I love playing card games, but the rest of my family, the other 3 people, all would rather play a board game. So maybe the reason they're rolling the dice is to say, okay, well, you're the only one who wants a card game, so the one side will be for you, and then if it lands on a 2, 3, or a 4, we go with a board game. So it's almost like a majority rules, but they're still giving it a chance. They're still giving mom a chance. Instead of saying, no, mom, you can't do it, or we're not playing card games, we're just playing board games, they're still giving the one to her and the other 3 to the other ones. And that could be anyone. I just gave an example so it made a little more sense. So to roll a 1, so a probability of a 1 is a 1 out of 4 chance. The probability of 2, 3, or 4 is a 3/4 chance because 3 of the 4 sides are showing a 2, a 3, or a 4. Okay, so they've already got some of these started for you. For the B, it's 0.75 or 3/4. In fact, you can write, if you could go ahead and write 3/4. I know it's little, but we talk so much about fractions that I think it's good for you to see it as a fraction. And it's also good for you to see that 0.75 is 3/4 and 0.25 is 1/4. Okay, so if Monday is a board game and Tuesday is a board game, that's a 3/4 chance times a 3/4 chance, which is 9/16, which is 0.5625 or 56.25%. That means that the family has a 56.25% chance of playing a board game on both nights. Okay, because it's a 3/4 on Monday, it's a 3/4 on Tuesday. That means that of all the options there could be, 56% of the options lean towards board game, board game. Now, for the next one, we've got BC. So what's the probability that we would have a board game and then a card game? Well, it would be 3/4 times 1/4, which is 0.1875. It's already written in there. And to leave it as a fraction, it's going to be 3 out of 16, which is an 18.75% chance. Now, the thing that I think is interesting about this next part is, what if it was a card game the first night and a board game the second night? We still have the fractions 1/4 and 3/4, but they're switched. So do you think it'll be the same probability? Yes, it's a 3/16 chance, which is 0.1875, same as before, which is 18.75%. So if you think of it, these are actually very similar outcomes. It's just that one night we played board games, the other night we played card games, and in the next one it's switched. We played a card game first and then a board game. Okay, the last one though, this one is not a very good chance of happening. If you think about it, the chances of mom winning both nights, like she just has one side of the die. That's just a 1/4 chance on the first night and a 1/4 chance on the second night. But if you multiply them together, again, if you forget how to multiply fractions, it's 1 times 1, which is 1, and then 4 times 4, which is 16. So if you forgot how to multiply fractions, again, you're going to have to ask on that. Okay, so now if you actually change 1/16 to be a decimal, it's just 1 divided by 16, and then we can change it to a percent. That's 0.0625, which is only a 6.25% chance of happening. Okay, so board game is 56%, about 56%. Board game card game is about 19%. Card game board game is another almost 19%. And then to play 2 card games is only a 6% chance, approximately. Okay, and that's what we just did. We just calculated. So the board game is right there. The board game card game option is right here. Card game board game is here. And card game is here. Okay, again, if you don't have a calculator or you forget how to multiply these fractions or change them to decimals, be sure to ask how to do that. All right, so what is the probability that there will be exactly one night of board games over the 2 nights? So actually 2 of these, board game, card game, and card game, board game, each of these have exactly 1. exactly one board game. So we can add those together because it's not just an 18.75% chance. It's 18.75% plus another 18.75% because we're really kind of like doubling our options there if you think of it like that. Because I'm okay with either one of those options as long as there's one night of each. So that is a 37.5% chance. Okay, and then once you do your summary, that is a wrap on lesson 6.